In this video, we're going to go over a test of comparing two different means. To give you an example of what I mean, here are three different claims that we could test using a two-sample t-test. For example, this second claim says that ISU male graduates have a greater starting salary than their ISU female counterparts. We could test that by sampling, say, 100 ISU male graduates, asking them what their starting salary is, and then comparing that to a sample of women's starting salaries. We could also do it for, say, the cholesterol levels of people with and without diabetes. So we would sample, say, 200 people with diabetes and 200 people without diabetes and examine their cholesterol levels to see if they're statistically significantly different. Now, I don't have to sample the exact same size. I could do 100 people with diabetes and 300 people without diabetes. The way I construct this test will take into consideration that your sample sizes may be different between the two groups. Just like the proportion test, the new parameter that we're interested in is the difference between the two groups. That is, average 1 compared to average 2. So we're looking at the total difference between these two groups. This is a few examples of what I'm talking about. So we're comparing the average SAT scores of men to the average SAT scores of women. If the test finds that the average score for men is greater than the average score for women, we are not saying that all men have a greater SAT score than all women. We're just saying that the average man has a greater score than the average woman. But again, you would need to go out and collect data to verify that that claim is true. When you collect the data, the three main components that you're going to need are the sample averages for both groups, the sample standard deviations, as well as the sample sizes for each of the groups that you've observed. Now, this is the formula that I will be using to calculate a t-score to run this test. The book uses a slightly different standard error. It uses what's called a pool standard error. Much like with proportions, if we assume that the two groups are the same, then we can pool them together and get what's called a pooled standard deviation. The book follows that formula. I'm going to show you how to calculate the standard error when we don't pool the two groups together. That is, we're not assuming they're the same distribution. Now, when your sample sizes are very small, there will be a difference between these two methods. But when your sample sizes are very large, there's not going to be much variation between the pooled method and this method that I'm showing you here in this video. So you should be fine in all of your homework problems choosing one calculation method over the other. If you prefer the pooled method, then you can do that. If you choose this standard error method, then that's fine as well. If you run into any problems in your homeworks calculating the standard error, then just let me know. The method I'm using to calculate the standard error keeps the standard deviation of the samples separate, so it doesn't pool them together, and it divides that standard deviation by the sample size of its own group, and then we square root that whole term. You can see here that I've squared that standard deviation, so it's fine that I square root it again to get it back into the units that I need. To calculate the t-score, then, I'm going to use that standard error in my denominator. What goes on top, then, is my sampled difference minus my hypothesized value. And just like with the proportions test, for most of these problems, we're going to assume that there's no difference between these two groups. So this hypothesized value is almost always 0. And what you put on top is mostly just the difference between your two samples. So this is the sample for group 1, and this is the sample average for group 2. So let's quickly try a problem so you can see how this t-test might be implemented. Here, a student is taking two routes to class, Route A and Route B. She walks there every day. to the same place, and each day she randomly chooses a different route, and so that she walks each route 20 times. For Route A, her average time is 44 minutes. For Route B, her average time is 47 minutes. Now, some days she walks faster and some days she walks slower. The standard deviation captures that variation for each of the two routes. You can see that at Route A does appear to be faster in this sample of 20 walks. But we want to know, is it statistically different? That is, it's not just due to sampling variation. We can test this, and we'll test this at a really small significance level. That means we're requiring a very large amount of evidence. So the first thing we want to do is we want to set up our null and alternative hypothesis. Here, I've put Route B first because the average for Route B is higher than Route A. You could put either one first, and your conclusion should still be the same. The alternative hypothesis, then, is that if Route B is slower than Route A, we would have a positive term here. So if you put Route A first, then your alternative hypothesis would be that you would have a negative term. So it's important to set up this alternative hypothesis correctly because that's going to affect how you calculate your p-value. The next step we want to do is we want to calculate the t-score. Again, I put Route B first just because it's larger and so I can be consistent in my interpretation. So Route B goes first, Route A goes second, and then I subtract off the hypothesized value that there is no difference between these two routes. I'm then going to divide by my standard error of the sampled differences. That is just the standard deviation for Route A squared, and then I divide by my sample size, which was 20. But I also do this for Route B as well. So I'm going to divide first and then add these two terms and square root last for a final t-score of 2.0952. The degrees of freedom we're going to follow is that provided in the book. The degrees of freedom is just the sample size for group 1, group 2, subtracting off the fact that we have two parameters, the average of group 1 and the average of group 2. So our final degrees of freedom is actually going to be 38. The probability we're interested in is the probability then that we see the observed difference, which is 3, that we do, or something greater than that, a difference that's even greater than 3 minutes. This is the same as saying that we observe the z-score that we do, or something greater than that. The TI calculator we can use to calculate this p-value, again, we're looking at an upper tail since we're looking at everything greater than this t-score. And so we're going to use that value, that t-score, as our lower bound. The upper bound is the highest number the calculator can take, which is 10 to the 99th, and then the last number is our degrees of freedom. We could also use Excel, and the Excel formula gives us everything that's below a z-score, so we're going to do 1 minus the t-distribution to get us everything that's above this t-score. And so again, we put in the t-score, the degrees of freedom, and then 1 indicates that we're looking at the cumulative distribution function. Either of these two methods are going to give you the same or approximately close p-values. So our conclusion in this is to compare the p-value to the significance level. Our significance level was really small, implying we really required a lot of evidence, a large difference between these two groups. Because our p-value isn't small enough, that is, our p-value is greater than our alpha level, then we must fail to reject that null hypothesis. While we do find a difference between these two routes, we just don't have enough evidence to suggest that Route A is actually faster than Route B. Now again, we'll note that our sample says that Route A is faster than Route B, but this may just be due to sampling variation. If we were to sample again, we might see that route A is actually slower than route B. So this is the formula that I use to construct my t-score and ultimately use to calculate my p-value. Again, your book shows you a different method for calculating that standard error, and their method is called a pool standard error. In a few instances, you may find differences in these two types of standard errors. And again, if there's a problem with your homework in how you're calculating the standard deviation, or if you're having problems with standard rounding errors, then it may be because of the two different methods for calculating the standard error. So just let me know if you're having problems with rounding errors. In the next set of videos, I'm going to go over a few more examples so you can see how this calculation works.